Now we've got to the stage where we can show that the triangle we wish to construct, namely this one here, has sides in the ratio √6 to √6 to 4. We're going to be concerned with three triangles. We're going to be concerned with this triangle, the equilateral triangle, the face, because we're going to need to know the length of the altitude. Then we're also going to need to know the length of the altitude of the tetrahedron. And then we can work out the radius of the tetrahedron, because it has a circumsphere surrounding it, which we can't see, but it is a radius. And once we know the altitude, we know that's 1/4 of an altitude of a tetrahedron. And we know this is 2/3 of the altitude of the equilateral triangle. So we'll be able to use Pythagoras to find out the length of that radius in there. So let's get started. For convenience, we're going to call the side or the edge length of the tetrahedron 2. Then that clearly is going to be 1. And this is going to be √3, because 4 take away 1 is 3, and the square root of 3 is √3. So now we've already found something that we need to know. Now we're going to refer to this triangle in which we can find the altitude of the tetrahedron, which is here. And this is 2/3 of √3. And this is 2. So let's do our calculations in here and see if we can work out what that length, which is the altitude of a tetrahedron, is. Well, we're going to want the square root of 4 minus 4/9, 2/3 squared, times 3. And we're going to want to put all of that in a bracket. A straight line is a bracket, and there's our square root. Well, that's 4/3, and this is 12/3. So we're going to end up with √8/3 for the altitude of the tetrahedron. So now we're well on our way. We can look at this triangle down here, and we can say that this little bit, that little bit in there, is 1/4 of the altitude. So that's 1/4 of √8/3. And then this length is our friend 2/3 of the altitude of the triangle. So that's 2/3 of √3. And this is the radius, which represents that line there. Well, it represents any of them, but that one, or that one, or that one, because it's all symmetrical. Well, once again, we're going to use Pythagoras. And so we're going to have, squaring this, 1/16 times 8/3 plus 4/9 times 3, and that's going to equal our radius squared. So we have 8s into that go once and into that twice, so we have 1/6 plus 4/3 equals r squared. Now that's 8/6, so altogether we're going to have 9/6, or 3/2. And so our radius is going to be √3/2. Now, how well does that help us? Well, in this case, we've got our triangle like this. We found the two radii. This is just a sketch, of course. And we know that this is √3/2, and we know that root 3 over root 2, and that's root 3 over root 2, and this is 2. Well, we want that to be 4, because it's going to be more convenient to construct a shape where that length is 4. So we'll double this, and we'll double that, and we'll double this. And because root 2 goes into root 2 times, we have exactly what we want, which is root 6 for this one, root 6 for that one, and 4 for this one here. So we've established and shown what we wish to show, that the triangle we need to construct to make these nets has the ratio root 6 to 4, and you can scale it up or down as you please to make these shapes as large or small as you like.